Can you guys hear the beep when it does that too, like through the thing? All right. So the last time we talked, we started talking about inequalities and we were solving them like equations. And we had things like less than, right? We had things like x is less than a, or x is less than or equal to a, or x is greater than a, x is greater than or equal to a. Do you guys remember that? That's the stuff we talked about. And we graphed them and we solved for them to get x all by themselves. And you guys didn't have to graph them in homework, but I showed you, and I remember specifically telling you, I'm showing you how to write these in interval notation. I'm showing you how to graph them because we're really going to need it for later this week. And now later this week has arrived, right? And so we're moving on to what we call compound inequalities, right? So when we had this, we could talk about it like if I had x is less than 3 and we graphed that, we would have a point at 3, right? This is just less than, there'd be an open dot and it would go forever in the less than 3 direction, right? If I had x is less than or equal to 3, it would be the same thing, right? Only we'd have a closed dot at 3 and it would be everything in the less than or equal to direction, right? Same thing if this was x is greater than 3 and we were graphing it. Usually I like to do different colors for this, but this is all repeat stuff, right? I'm saying that I have an open dot and x is starting at 3, doesn't include it, but it includes everything that's bigger than 3, right? And if we did this one as x is greater than or equal to 3, solid dot, as we're including 3, bam, right? And we did a bunch of problems and you had to get x by itself, right? We had to solve them like an equation and you would get x by itself so that you would know what x is. And we are moving on from that. We're doing today what we call compound inequalities. And compound inequalities compound. It looks like I made 2 N's, but that was a U. Inequalities. My most difficult thing as a person with a math degree is spelling. I used to be really good at all that. Like I was a good writer and I could spell really well and I could do stuff. But now I am so math focused all the time in my whole life that I've lost the ability to spell. So a compound inequality is defined as 2 or more inequalities. I would cry if it was more than 2, but 2 or more inequalities, things that are not equal, graphed together on the same number line. On the same. This must be really boring to watch in the video where you're just waiting for me to finish writing out a sentence. I mean, it might be boring for you right now too. I don't know. Hopefully you're writing them along with me. So there's 2 types. When we're talking about compound inequalities, you have 2 types. You have an or type and you have an and type. Those are our 2 types of compound inequalities. Inequalities, you can always tell which type they are by looking at the graph. Or if, well, one or inequalities always say the word or. So you pretty much know what you're dealing with an or inequality, because unless somebody stupid wrote the question, which would be me, most of the time. If it's a stupid written question, it's probably one I wrote myself. It's going to say the word or in it, right? Or inequalities always graph in opposite directions. So if they aren't graphing in opposite directions, you did something wrong. I can usually tell you what the problem was without even looking at it, that something that you did wrong was probably you multiplied or divided by a negative number and didn't flip your sign. Usually that's the mistake you've made. We're going to go over each type. We're going to start with the or type of inequality. So we're going to call that type 1. Type 1 is or, right? When we want to solve an or problem, an or inequality or problem or whatever, you are going to solve each part separately, and then you're going to graph them on the same line. Think about or as only one piece has to be true for the whole statement to be true, right? That's kind of a logic thing. You'll see that a lot in like computer science, but you kind of see it in life too. Do you want milk or do you want juice? You want one or the other, right? You could have both, but only one or the other has to be true in that scenario. That's a bad scenario though, because it's not really a true or false statement, but it's the only thing I could think of right now because I'm thirsty. So let's do some examples of our type 1, our or problems. If I have, say, 3x plus 4 less than or equal to 10, or 5x is greater than 45. Now, these are not complete problems. I have to have my x's isolated, right? My variable has to be isolated, just like earlier this week when we were solving for simple inequalities, right? We had to get that x all by itself, and we still have to do that. Now we have to do it twice on these, right? Because we have two separate problems. So I'm going to look at what's going on this side of the inequality, because that's where my x is. That's where my variable is. So I have 3 being multiplied to x. I have 4 being added to x. So I'm going to get rid of those things. I'm going to start by subtracting 4 from both sides. Here I'm going to be left with 3x is less than or equal to 10 minus 4, which is 6. Now I still don't have x by itself. I've still got that 3 being multiplied to it. So I'm going to go ahead and divide out the 3 on both sides, and I will have x is less than or equal to 6 divided by 3, which is 2. And now we're going to work this side, right? We've got this one solved for x. This one problem is already solved for x. So we can move on to the other problem and go figure out what that is. And the only thing that's happening to this is that we have 5 being multiplied by that to that x. So we're just going to go ahead and divide out that 5 on both sides, right? And I will be left with x is greater than 9. So I have my 2 pieces of information here, right? I have x is less than or equal to 2, and I have x is greater than 9. These are conflicting, but it doesn't matter because we're saying that one or the other has to be true. If I have a number line, the only numbers that I care about right now on this number line are 2 and 9. Make sure that you write them in the right order. If this were the 2 on this side, make sure you still have the 2 first and then the 9, right? Make sure you write them in the order that numbers actually go. So I have the 2 pieces of information I need on this number line. On a regular number line, there'll be a whole lot more numbers, but the only ones you care about are the ones you just solved to. So now we're going to look at these pieces of information we have. We're going to graph both of these on the same number line, right? I have this piece right here that says x is less than or equal to 2, right? So that means it could be equal to, so I'm going to have a solid dot here at 2. And it is going to be everything that is less than that. My other piece of information that I have is that x is greater than 9, right? Doesn't include 9, so I'm going to have an open dot at 9, and it is going to be everything bigger than 9, right? That's what I mean when I say they graph away from each other when they're OR problems. They always go in opposite directions. If they're going in the same direction, you probably screwed up, or they're 2 lines that sit on top of each other and you're going to want the one that includes all of it. But that's a rare occurrence. If I want to write this in interval notation, and I believe that you'll want to in Delta Math, I'm not sure. Look at this. This piece right here starts at negative infinity, right? It goes all the way forever and ever and ever. And it stops at 2 and includes 2. So I'm going to have a bracket right there. Union 9 to infinity. That just means we connect these, right? Both of them are true. These are all of my solution sets, right? In the same respect that when I was dealing with, if I just had x is less than or equal to 2, all of the things that make that true are everything that's less than 2, right? Let's look at one more of these OR problems, and then we'll move on to some AND problems. Sound good? I'm trying to see if I have one that can make me have to multiply or divide by. Ooh, I like this one. The reason I like this one is because it has variables in more than one spot. Or does it? No, it doesn't. But I still like it. If I have example number 2, negative 3y plus 8 less than or equal to negative 7, or 10y minus 3 less than or equal to negative 33. I like this one because it's going to require you to multiply or divide by a negative, so you can see that in action and how it would screw it up if you didn't. So we have to solve these individually. If I look at this problem right here, I have a couple things happening to my variable. I have 8 being added to it. I have negative 3 being multiplied to it. We're going to start with learning how to speak. We're going to start with what is being added or subtracted, right? So I have 8 being added. To do that, I'm going to use inverse operation, which is minus 8 from both sides. And I'm going to get negative 3y is less than or equal to negative 15, right? Minus 7 plus minus 8 is minus 15. Now I still have that negative 3 that's being attached to that y. So I'm going to go ahead and I'm going to just divide everything by negative 3. When I do that, I'm left with y. Switch your sign. If I don't switch the sign, my arrow is going to go the wrong way when I try and graph this. So flip your sign around because we're multiplying or dividing by a negative. So we're going to now have is greater than or equal to 15 divided by 3. I can lose the negatives because they're both negative. It's going to come out positive. I'm going to have y is greater than or equal to 5. We're going to work this side now, right? What's happening to this side? We have a 3 being subtracted. We have a 10 being multiplied. We're looking at what is happening to our variable, right? So I'm going to start by adding 3 to everything. Plus 3. And I'm going to get 10y is less than or equal to negative 30. Now I've just got that 10 being multiplied to it. So I'm just going to divide by 10. I don't have to flip my sign because I'm not dividing by a negative number. So I'm going to be left with y is less than or equal to negative 3, right? Negative 30 divided by 10 is negative 3. So when we go to graph these problems, the only numbers that I care about right now are negative 3 and 5, right? They're the only numbers I care about. Y in this case is greater than or equal to 5. It has that line under it, which means we've got a solid dot and not an open dot, right? At 5. It's saying that it is bigger than 5. So it includes 5 and it is all things larger than 5. Here, we're saying y is less than or equal to negative 3. We have that line under it, so it is a solid dot, and it is everything, boom, that's less than 3. That's your graph, right? Or problems graph away from each other. Think about this. If I had forgotten to switch this sign, right, this would be going in this direction, right? Had I forgotten to flip my sign, both arrows would be going in the same direction. That's why I said I can always tell where the mistake is if you have an or problem and they're going in the same direction. It's almost always that you forgot to flip the sign when you multiplied or divided by a negative. Let's look at and problems. Type 2. Type 2 problems is and inequalities. To solve and inequalities, well, to solve one where they're written separately, you'll know because they say and in between them. So, well, I got to flip my page around to see all my problems. Solve and problems. If the and is written, if they are presented, as two problems, as separate problems, right? And you'll know if they are, they'll say and. If they're presented as separate problems, solve them separately, graph them together. If they are condensed, you're going to solve it all as one problem. And I'll show you what I mean. It's so weird to be writing, like this is a black tablet that I write on. I can't see what I'm writing on the tablet. I have to look at the screen while I'm writing down, and it's just a really weird thing to get used to doing. I mean, I've been doing it for like a year and a half now, but I hadn't done it in a while. So let's look at some examples of what I mean by and. Our or problems, when we graph them, they graph away from each other. Our and problems are going to graph into each other, right? Because both statements have to be true. Where or statements, only one had to be true at any given time. For and statements, your solution set always has to be true for either problem. So let's look at an example. If I have 2x plus 3 less than negative 9 and 8x minus 2 less than 30. So this is the circumstance where they're written as two separate problems. Notice they say and in between them. So you can know that they're going to graph into each other just by seeing that word, right? We're just going to go ahead and solve each of them individually. Here I have 3 being added, 2 being multiplied. So I'm going to start by subtracting 3. And I would have 2x is greater than negative 12. And then I've got the 2 being multiplied to it. So I'm going to go ahead and divide out the 2 on both sides. And I get x is greater than negative 6. Right? I didn't multiply or divide by anything negative, so I didn't have to flip the signs. Here, I have 2 being added, 8 being multiplied. So I'm going to start by adding 2 to both sides. And I get 8x is less than 32. I still have that 8 being multiplied to it, so I'm going to divide both sides by 8. And I'm going to have x is less than 4. Those are the only 2 numbers I care about. And when I go to graph this, I'm going to focus on negative 6 and 4 on my number line. Your number lines, they'll be presented to you as number lines. They'll have a lot of numbers on them. The only ones you're going to care about, though, are negative 6 and 4 and what's happening there. In this case, we are saying that x is greater than negative 6, not greater than or equal to. So we're going to have an open dot at negative 6, and it is going to be everything greater than, right? But this also has to be true at all times on an and problem. So we know that x is less than 4, not equal to, so open dot, and it's going to be everything in here, right? They're going to come together. They graph into each other. Our solution set, when we're writing this in interval notation, is just parentheses, because we're not including negative 6, all the way to 4, which gets a parentheses because we're also not including 4, right? It's not equal to 4. Does that make some sense? What if the and isn't written? How will I know? How will I ever know it's an and problem if they don't write the and? Well, I'm going to show you, because I would not sell you something without letting you test drive it first. What if I have another example? I love examples. What if I have 4 less than 3p? I hate it when the variable's p. I usually try and change it to x, but I didn't do it this time. I just wrote that sucker out. If I have something like this and it's written all as one equation and you got like an x thing in the middle, that is an and problem, right? It's saying that, I know, I hate when variables are p because I say p over and over and over again. So we are going to solve this as one piece, but think of every inequality as an equal sign, right? If I do something in here, I have to do it to each section, right? But we're still looking at what's happening to our variable, and our variable is in this middle part right here. So we need to go, well, what's happening to P in here? 4 is being added to it. 3 is being multiplied to it. So we're going to undo those things. We're going to start by subtracting 4. But I can't just subtract my 4 from here. I also have to subtract it from this side and this side. So this becomes 4 minus 4. Well, that's just 0. Less than 3p. That zeroes out. And then I have 19 minus 4, which is 15. This isn't solved yet because I still don't have the p by itself in the middle, right? I can't believe I just said that sentence. So we're going to have to divide everything by 3. Here is 3. There a 3. Everywhere a 3. 3. Right? 0 divided by 3, 0. Less than 3 divided by 3 is 1, so I'm left with just p here. Just p. 15 divided by 3 is 5. If you look at this, it kind of tells you exactly what your graph is going to look like, your whole solution set, right? It's saying that P is between 0 and 5, right? It kind of tells you what your solution set is. All of the numbers that P can be to make this true lie between 0 and 5. And when you go to graph that, bam, what do I care about? I care about 0. And I care about 5, right? What's my graph going to look like? Well, 0, it doesn't include 0, right? There's no equal to. So we have an open dot at 0, and it's going to go in that direction because it's greater than 0. But it is also less than 5, so open dot at 5 going in that direction. So my solution set just runs from 0 to 5. Does that make some sense? I've got something new for you today. I need all of you guys to do this before you leave. I'm about to put a link into the Meet. You're going to get one of these every single class period, and you're going to have to do them every single class period. They are worth 50 points. How much is a homework worth? 100 points. So they're worth half a homework. It will never be one or more than 1 or 2 math questions, but you'll always have a question. One of your questions will be, what's your name? One of your questions will be, is there something that you didn't understand from this lesson that you need to know more about? And one of them will be a math question. Just doing it will get you your first 25 points, right? I know, they're like super generous, right? Wow, Miss Hoy, you're the best. I'm going to stop recording this because I'm